This is Green River College, Physics 114, Chapter 1, Sections 2 through 3, Units. Part 1, Fundamental Dimensions. I am your instructor, Mark Davidson. So, we're dealing with units, and units answer a fundamental question. What are we talking about? So, for example, I once went into a grocery store, and you know there are those pre-printed plastic tags that have the price of produce on them. Well, the manager wanted to change the price of spinach. So they took a small paper bag and wrote on it, spinach 99 cents, and put it over the small plastic tab. There's a problem with this, though. There's more than one way to buy spinach. You could buy it by the bunch. 99 cents per bunch would be pretty expensive spinach. You could buy it by the pound. That would be reasonable. You could buy it by the crate. What a deal! You could even buy the entire display, which I don't think is what the manager had in mind. This ambiguity comes from the fact that the manager got the units wrong. Spinach 99 cents is not a price. It's a quantity of money. Spinach 99 cents doesn't really mean a whole lot. It wouldn't mean anything even if we put our monetary system on the spinach standard. Units are how we measure things. And the things that we measure are called dimensions. We're not talking dimensions like three-dimensional space. We are using the term dimension to indicate, again, something we measure. There are certain fundamental dimensions that we can use to construct all other dimensions from. One of those dimensions is length. The thing that makes length a good fundamental dimension is that it's a property of objects. For example, if I were to take a ruler and measure the spine of a book, I'd get a number. I could go across town and measure again, and I'd get the same number. I could go to France and do it again. I'd get the same number. I could go to the International Space Station. I'd still get the same number. This is because the spine of the book, the length of the spine of the book is a property of the book. Length is a property of objects. The units of length are how we measure length. We've got many ways of measuring length. Inches, feet, yards, miles, meters, centimeters, kilometers, furlongs, parsecs. A long time ago in a galaxy far, far away, parsecs were a measure of time, but here and now they're a measure of length. Light years and other ways to measure length. Another fundamental dimension is time. Suppose I had a music box, and I gave its key half a turn. I could take a stopwatch and measure how long it played, and I would get a number. I could go across town, time it again, I'd get the same number. I could go to France, I'd get the same number. I could go to the International Space Station, I would still get the same number because time measures the duration of processes. And that is what makes it a good fundamental dimension. We have several ways of measuring time. Seconds, minutes, hours, days, weeks, fortnights, months, years, centuries, and other ways of measuring time. Now, one thing we should notice here is that with length, we have imperial units, inches, feet, yards. We also have metric units, meters, centimeters, kilometers. But with time, we have minutes, seconds, minutes, and hours. Those are all imperial units. We don't have any metric times listed. And the reason for this is that after the French Revolution, the revolutionaries developed a new set of weights and measures, the metric system, that included both metric length and metric time. Metric time was so unpopular, though, that almost no one uses it. That's why we're stuck with time units in base 60, which comes from ancient Egyptian numerology. There are some people who use metric time to this day, but not many of them. Something we measured in the scaling lab was weight. So, suppose I took my book and weighed it. I'd get a number. I could go across town. I'd get the same number. Go across town, weigh it again. I'd get the same number. I could go to France, get the same number. I could go to the International Space Station. Okay. We don't get the same weight. It goes to 0, and that's a problem because the weight is not a property of an object. It's a relationship of the object to whatever planet it's on. So weight is not a good fundamental dimension. Instead, we use a thing called mass. Well, here's the thing. Mass is a theoretical quantity. You really can't measure it directly. It violates our notion that dimensions are things that we measure. But it is a property of objects, so it is one of our fundamental dimensions. We have several units for mass: grams, kilograms, milligrams, slugs, pound masses, and other units for masses. Slugs and pound masses are imperial units for mass. And we're kind of late to the game. Imperial units were established before Newton did his thing, so the distinction between weight and mass wasn't clear. And truth to tell, to this day, if you get 5 pounds of potatoes, you don't care whether pounds are weight or mass. You only care that you're getting the right amount of potato. The metric system came after Newton, so it had mass units from the get-go. After the imperial system, after that, the imperial system had to incorporate mass, and so they created slugs and pound masses. So, lengths, time, mass are all fundamental dimensions that we will use in this class. The National Institute of Standards and Technology, NIST or NIST, has 4 more fundamental dimensions. Electric current. This was a surprise to me. I thought it would be electric charge that would be the fundamental dimension, but electric charge is very hard to measure. What experimentalists and engineers tend to do is measure electric current and then derive what the electric charge has to be from the electric current. And they do that because current is easier to measure, and experimentalists and engineers like things that are easy to measure. You would say that, you could say that theorists one where mass is concerned, and that experiments one where electric current is concerned. Another fundamental dimension is thermodynamic temperature. That is any temperature scale that measures absolute zero as 0. Celsius and Fahrenheit do not do this. The Kelvin scale does. Another fundamental dimension, the amount of a substance. That is to say, the number of atoms or molecules of a substance we have. We tend to measure that in moles, and you'll learn more about that in chemistry. And then finally, we have luminous intensity, which really surprised me because you shouldn't be able to construct fundamental dimensions from other fundamental dimensions. Fundamental dimensions should be the building blocks for the other dimensions, but you can construct luminous intensity from the first three fundamental dimensions with some solid geometry thrown in. What happened was this. Luminous intensity for a long time was difficult to measure, and various countries started coming up with their own standards for measuring it. After a while, technology caught up so that we could measure luminous intensity easily and accurately. At this point, NIST made luminous intensity a fundamental dimension to kind of twist the arm of other countries into adopting the American standard. So the reason luminous intensity is a fundamental dimension has more to do with international politics than science and engineering. So there you are, the fundamental dimensions. Next time we will look at arithmetic with units.